Section 4.3 is on page 165, talks about auxiliary equations with complex solutions. Recall from calculus the following series. So if I take e to the I theta based on this formula, that is 1 plus I theta to the 1 plus I theta squared plus I theta cubed I theta to the fourth, and the list goes on. Now, if I separate those, if I say that is 1 plus I squared is negative 1, I to the fourth is a 1, plus if I take I theta, I cubed is negative I theta cubed, I to the fifth is I theta to the fifth, and the list goes on. I will get this to equal 1 minus theta squared plus theta to the fourth minus theta to the sixth, and the list goes on. I'm not gonna write this in the summation. There's no need because the expressed is right there and right there. Oh, I forgot that. Oh boy. Over 1 factorial, 2 factorial, 3 factorial, 4 factorial, and the list goes on. So this is over 2 factorial, 4 factorial, 6 factorial. And here, this is over 1 factorial, over 2 factorial, 3 factorial, 5 factorial. So this will be theta over 1 factorial minus theta cubed over 3 factorial plus theta to the fifth over 5 factorial, and the list goes on. So if I split those into 2, by what I see there, the evens are really the cosine of theta plus I times, and the odds are really the sine of theta. So this stands only for direction, meaning that this never comes in the equation. This is the famous Euler's formula. So this I really never comes into play. We never introduce it in the problem. It's just for direction, like, you know, AI plus BJ. That's on the y-axis. Well, or the complex axis, however you want to see it. If the auxiliary equation or the characteristic equation has a complex root, if r equal alpha plus I beta, then I'm going to get y to equal e to the alpha plus or minus. We'll take one of them times t. That's going to be e to the alpha t times e to the beta t times I. And based on what we have up there, that's e to the alpha t times cosine of alpha of beta t plus I times sine of beta t. And we say the fundamental set is e, if you distribute that in, alpha t cosine of beta t, and e to the alpha t sine of beta t. Meaning any multiple of those will do, and there's the solution. Now, we want to apply that in 1 through 8, find the general solution, and this is a second order linear differential equation with constant coefficients. Every time that happens, we let y equal e to the rt, and we need two derivatives, y prime equal r e to the rt, and y double prime equal r squared e to the rt. So we get r squared e to the rt plus r plus e to the rt equals 0. factor out e to the rt, r squared plus 1 equals 0. E to the rt can never equal 0, so r must equal plus or minus the square root of negative 1, which is I, which means cosine of t, sine of t will form fundamental set, and the general solution would be a, the cosine of t, plus b, the sine of t, or any multiples of those. That would work. So, nothing new really. Same thing. Second order linear differential equation with constant coefficients. That's important. What if we don't have constant coefficients? That's coming up. That's a different chapter. And hopefully we're getting the hang of this. R squared e to the rt minus 10 r e to the rt plus 26 e to the rt equals 0. Factor e to the rt out, and you're left with r squared minus 10r plus 26 equal to 0. E to the rt can never equal 0. It must be that r squared minus 10r plus, I'd rather complete the square than use quadratic formula. You could use whatever you want. I think it's much easier this way. Half of that is 5 squared is 25. So I get r minus 5 squared equals negative 1, which indicates that r equal 5 plus or minus r, and y equal, in this case, e to the 5t times a, the cosine of t, plus b, the sine of t, would be, of course you could distribute that if you wish, that doesn't matter. That turns out to be the general solution. Not that bad at all. Same deal here, hopefully third time will be a charm. This is a second order linear differential equation with constant coefficients. You let y equal e to the rt, y prime, and y double prime. So hopefully you're getting sick of this, which is a good sign. To get sick of something in math, that means you really get it. But I'm not going to stop writing these out so that we never are confused on where anything comes from. That cannot equal 0. It must be r squared plus 2r negative 5 half squared is 1. R plus 1 squared is negative 4. R equal negative 1 plus or minus 2i. So the general solution is, we don't use A, we use C, right? I keep forgetting. We leave A for the particular solution, and that's how we separate between them when we find the C1, C2. It doesn't really matter. It's the same thing, right? So this is going to be e to the negative t times C1, the cosine of 2t, plus C sub 2, the sine of 2t. That's really how we find the solutions. And what could happen, they could give you initial conditions, and let's get those out of the way. Good practice, a bit more work than the traditional, but not that big of a deal. Second order linear differential equation with constant coefficients. Let y equal e to the rt, y prime is r e to the rt, y double prime is r squared e to the rt. So I have e to the rt times r squared plus 2r plus 17 equal to 0. E to the rt cannot equal 0. It must be that r squared plus 2r plus negative 17. Take half of the middle number. Okay, I need to squish that. I have plenty of space. There. Take half of the middle number, which is 1, and square it. That would be r plus 1 squared equal negative 16. So r equal negative 1 plus or minus 4i. The general solution is y equal e to the rt, e to the negative t. By the way, something I want to start mentioning really quick. C sub 1 cosine of 4t plus C sub 2 the sine of 4t. Now if I take the limit as t approaches infinity, this, it circulates, right? an s. That's the sine of t. This circulates back and forth, oscillate. This will go to infinity, and here the limit as t approaches infinity, this would be damping force. It will devastate those two, and this will go back to equilibrium. Same thing here, e to the negative t. If I take the limit as t approaches infinity, recall that exponentials dominate over anything except factorial. Factorial doesn't come for us in our applications, so exponentials are the dominating functions for us. Now, if I take y of 0, that is c1 times 1, e to the 0 is 1, that's it, plus 0, and that equal a 1, so c1 equal 1, got it, that's a 1, and y prime, if I take a derivative, it's going to be the product rule, negative e to the negative t times cosine of 4t plus c sub 2 sine of 4t, and e to the negative t derivative will be negative 4 the sine of 4t plus 4c sub 2 the cosine of 4t. So those derivatives are a bit lengthy. If I put a 0 in, that's a 1, that's a 1, plus 1 times, that's a 0, plus 4c sub 2, and that equals a negative 1. So I have 1 plus 4c sub 2 equal negative 1, which indicates c sub 2 equal negative 2 over 4, which is negative 1/2. So here the general solution would be, and let me just give myself a bit more space. Oh, come on. No, doesn't like it. There we go. And I would say y equal, so we got e to the negative t times the cosine of 4t minus 1/2 the sine of 4t. That would be the exact solution, or explicit solution, in this case, satisfying these cases. And one more to go. Again, if I look at a second order linear differential equation, it doesn't matter what the order is, with constant coefficients, we let y equal e to the rt, and y prime equal r e to the rt, y double prime equal r squared e to the rt, then we get r squared plus 9 times e to the rt equaling to 0, e to the rt cannot equal 0, r must equal plus or minus 3i, so we have y equaling the c sub 1, the cosine of 3t, plus c sub 2, the sine of 3t as a general solution. Oops. And I could say y of 0 equal c sub 1, and that equals a 1. Very good. In this case, just happened that way. And y prime will be negative 3 the sine of 3t plus 3 c sub 2 the cosine of 3t, and if I take y prime of 0, I'll get 3 c sub 2 equal 1, c sub 2 equal 1/3, and that indicates that my solution is that y equal the cosine of 3t plus 1/3 the sine of 3t. That would be the solution satisfying those initial conditions. One more I wanted to elaborate on. It's a very important application that's going to be coming up for us. Keep in mind this is not a second order, but it makes no difference what the order is. This is a linear differential equation with constant coefficients. I'm going to let y equal e to the rt. In this case, I need 3 derivatives. Well, not that big of a deal, just a bit more work. And now e to the rt times r cubed plus 2r squared plus 5r minus 26 equal to 0. E to the rt cannot equal to 0. It must be that r cubed plus 2r squared plus 5r minus 26 equal to 0. This doesn't factor, not a problem. We took pre-calculus or college algebra. We know the factors of this are 1, negative 1, 2, negative 2, 13, and 26. Well, 1 doesn't work obviously, and negative 1 doesn't work because 26 is too big to overcome to match. So let's try 2. Does 2 work? 1, 2, 5, and negative 26. You could plug it in and see 8 plus 8, that's 16, plus 10, that's 26. That works. So drop the first number, that's a 2, that's a 4, 2 times 2, that's 8, that is 13, that is 26, that's a 0. So I'm left with r squared plus 4r plus 13 equals 0. That doesn't match, right? That doesn't factor, I mean. So what we do, we go on the side, say, alright, well, we already have r equal to, and we have r squared plus 4r plus half of the middle number is 2 squared, that's a 4. That's r plus 2 squared equaling a negative 9. Square root both sides and subtract 2. And we get e to the 2t. And here we're going to get e to the negative 2t cosine of 3t and e to the negative 2t sine of 3t would form the fundamental set, meaning any combination with those would do. So that is c sub 1 e to the 2t plus c sub 2 e to the negative 2t cosine of 3t plus c sub 3 e to the negative t sine of 3t would be the general solution. If you remember those, the upper bound, lower bound, the card rules of signs, and factoring polynomials. That was a whole chapter back in your previous life. Section 4.3 on page 172. The homework is 1 through 19 every other odd, 21 through 27 odd, 29 I did B, you're going to do A and C. And that concludes this section.